intermediate value theorem. Objectives. Finally, this lesson you should be able to state the intermediate value theorem, use the intermediate value theorem, also known as IVT, to prove the existence of zeros. So let's talk about what it is. In general, the intermediate value theorem is a fundamental result which tells us that a continuous function cannot skip values. This means if I know I have a continuous function and I have 2 points on a continuous function, let's say I have a point here, -2 and 1, and a point up here, 5 and 8. What the intermediate value theorem says that every value from here to here, from 1 to 8 on the y, must be taken. Which just means that if I try to connect the continuous function from this point to that point, I'm going to have to hit every point between the y values 1 and 8. So no matter what type of function I draw, if it's continuous, I'm going to have to hit every value. So I could draw a line like this, right? All the y values taken. If I go up and go down crazily, I hit more, but I still hit all the points between there. That's kind of what the IVT says. So let's look at a more formal definition. Intermediate value theorem. If f of x is continuous on a closed interval from a to b, then for every value m between f of a and f of b, there exists at least one c value in ab such that f of c equals m. So again, in plain English, all that means is this. Given a closed interval, let's actually just pick points. Let's say 1 to 4. So my a value here is 1, my y value is 4, right? So if they give you this closed x value of 1 to 4, then for every m value between f of a and f of b, so they're saying f of a in this case will just be f of 1. So whatever that happens to be, it could be f of 1. That could be like a 2 or a 3 or some actual value, but when you plug in 1, what do you get? And when we plug in our other point, f of 4, what do we get? This will be f of 4. Let's just call that 6. Right, so what it says is there exists at least one c value in AB such that f of c equals m. So that they're saying if we pick some random point in the middle here, if we pick like, let's say it's random points in between 1 and 4, let's say this is 3.1, that there must be a y value for that 3.1 that falls in between those other two y values. So in here, my f of 3.1, let's look at the graph. It looks like it might be, I don't know, 5.4. That's all it's saying. If you have 2 points on the x value, if you know what their y values are, then every value between there has to be taken. So if you pick some random point in between these two values, there must be a y value that goes with it. That's kind of what it's saying in general. So again, keep in mind this theorem tells you an x value exists, but it doesn't tell you what that value is. Right? So I know f of 3 exists. I don't. F of 3.1 exists. I actually don't know the value. I kind of estimated here, but we don't really know. We just know there must be f of 3 that exists. This type of theorem is called an existence theorem. So they also want to add on to this what IVT tells us, what it doesn't. Right, so let's say I have these 1 and 4. Right, I have these points here from 2 to 5. I'm going to do another one right here to show you the same thing. 1, 4. Let's go exact same points, 2 to 5. What IV tells us is that all the y values from here to here must be used. Right? So if I tell you if we're going from 1 to 4, and it's a continuous function, it has to be continuous. You must say continuous, by the way. That's very important for IVT. Then all the y's from 2 to 5, right? The y values from here to here must be used. Now everything above it, it might be used. Maybe. Everything below it, maybe. But the ones between those two values must be used. Right? I kind of did this earlier, but I could draw different graphs. I could draw a graph like this, kind of like a straight line, maybe even a small curve, that only hits all the values from 2 to 5. But I could also go over here and go a lot more up and down. Still a function, right? See how it must hit these values? Right? Those are the ones that must be hit. But everything else above it might be hit. This one hits it, this one doesn't. So IVT only tells you the values in between must be hit, right? So if I give you 1 to 4, only the values from f of 1 to f of 4 must be used. That's what IVT is saying. Now let's look at the corollary to IVT. That's also very important. The existence of zeros. If f of x is a continuous function on a and b, and if f of a and f of b are non-zeros, and have opposite signs, f of a is positive, f of b is negative, vice versa, f of x has a 0 in a, b. In other words, the function must necessarily cross the x-axis. So let's kind of break this down again to what it means in words, in English. So they're saying, hey, you have a graph here, and I'd say something like, let's use 1 again. F of 1 equals some positive number, 4. Then you give some other point. F of 3 equals negative 2. So 3, let's go negative 2. Right, so this is 3, negative 2. This is 1, 4. What the existence zero theorem says is that since we're using that, it comes straight from IVT, right? Since if this is a continuous function, then I'm going to have to cross the x-axis at some point, right? That's what IVT says. Right? Every value from here must be used. So no matter how you graph this thing, you're going to have to cross the x-axis at least once. And that's the existence of zeros. If you have a negative value and a positive value, and I know it's continuous, right? Very, very important. Then you're going to have to cross the x-axis once. You're going to have to have at least 1 0. Now it's at least 1 0 because you could have more, right? What if my graph is like this crazy one I drew here? I have at least 3, right? I have 3, I shouldn't say at least. But remember the rule. Only the ones in between must be taken. So I know it happens at least once. Who knows what goes on? But at least once is the key. So you go from a negative to a positive or a positive to a negative like I did here. You're gonna have to cross the x-axis at least once. That's the existence of zeros. Keep in mind, I want you to notice that this is a special case of IVT. I think I kind of mentioned that, where we let m equal 0 so that there is some c such f of c equals 0. So right, this instance, the x value we pick, the y value we get is the 0 one. That's what we're looking for. That's all it is. So let's do an example using this. So here's some work done already, but here's the actual questions up here. Example. Show that the function f of x equals x cubed minus x plus 1 has a 0 from negative and negative 2, 0. So again, I actually did the work here, answered it all out, but I want to show you it step by step. So step 1, to show this, if you remember when we're talking about continuity, the number 1 rule before anything else is we have to show it's continuous. Right? Otherwise, IVT doesn't work, 0, like this is 0 doesn't work. Yeah, it has to be continuous to work. And so how do we show it's continuous? Well, we're going to use the 6 known continuous functions. So we just state it. So look at here. They gave us f of x equals x cubed minus x plus 1. What type of function is that? It's a polynomial function. And that's one of the 6 continuous functions. So we first start off by saying, first note that f of x is continuous on negative 2, 0 because f of x is a polynomial function. So that part's set. The very first one with all of these is showing that it's continuous. Because if you can't show it's continuous, then you can't use any of the theorems we want to use. So now that we know it's continuous, we want to actually use the IVT theorem. Now what I like to do is to actually get my values, to get like my parameters across. So I like to see on the side here, like kind of side work, I like to see what f of negative 2 is. I actually do the work right here to show you. I get negative 5. And I want to see f of 0 is. I do the work over here to show you, and I get 1. Now, do you remember what IVT says? Right, since it's a continuous function? Negative 2, 5. It's down here. Let me draw it so you can see it. And then 0, 1. 2.01. Remember, IVT says that, let me scroll down so you can actually see it. IVT says that since it's a continuous function, all the y values are going to be used, right? So everything from negative 5 to 1 must be used. Since it's a continuous function, all the y values in between those 2 points must be used, right? And that includes what we want, right? We're trying to find the 0, and that includes 0. Somewhere around here, it must have crossed a 0. Again, even if my graph's way crazier, at some point it must cross 0. So how do we show this with IVT? Well, like I said earlier, step 1, show it's continuous. So in this case, I would say f of x is continuous. It's continuous because it's a polynomial function, like we did earlier. Step 2, you want to evaluate, show the values you got that they give you as the parameters. So we have negative 2 and 0. So I'm going to show those equal. So I'm going to say f of 2 equals negative 5, and or since f of 2 equals negative 5 and f of 0 equals 1. Then, now it's kind of our choice. We can use IVT, we can use the zero property rule. So, the existence of zero rule, I should say. Well, based on these values, right, f of 2 is 0, f of 2 is negative, and f of 0 is positive. So, by IVT, you always gotta say IVT. If you're gonna use IVT, you gotta state it. Otherwise, we don't know why it's true. Right? There must be a 0. Now, we can't just say there must be a 0 between it. You want to make it fancy, so you must say there must be a c, because we have no idea what the x value is, such that f of c equals 0. So we're going to copy that right there. So there exists a c in between negative 2 and 0. This is just fancy writing for an element of negative 2, 0, so it's in between negative 2, 0, such that f of c equals 0. And that's kind of it. And then you could finish off by saying thus f of x has a 0. But that's kind of the crux of it. A 0 between negative 2 and 0. And that's how we use IVT. Right? So a little recap. 1, we show it's continuous, right? We have to say it's 1/6 continuous function. 2, I like to use what the endpoints they give us to show what the values are. Then you got to say your things is between those two values. Then you say by IVT, there's just a c in between the values you've given us, such that the thing I'm looking for exists. All right, so let's do it again. So another example here. Similar example. This time we're not looking for a 0. We're looking for a value of 3.5 in between this. So again, let me state what we're going to try to do here, right? So 1, we're going to show is continuous. 2, we're going to find the value. So if they give us on A and B, we're going to find f of A, and we're going to find f of B. We're going to find those two. 3, right, we're going to say that our thing we're looking for is in between those things. So we're going to say f of C was what we're looking for, is in between f of B and f of A. Now these could switch depending on which one's bigger. After we do that, we're going to say, oh, there's some C such that within our thing they gave us, such that by IVT, f of c equals whatever I'm looking for. That's kind of the process. So let's go through here. First, right, look at this function. It's a continuous function. It's a polynomial, so it's a continuous function. So I'm going to say f of x is a polynomial function so it's continuous. Alright, so I got it's continuous. I need that every single time. That part's done. Now off to the side here, I'm not going to put this in my main part of my answer. I'm going to do a little work. Let's see what our two endpoints give us. If I do f of negative 1, let's see what that gives us. So it's 2 negative 1 cubed minus negative 1 plus 3. So let's do this first. So I get negative 2 plus 1 plus 3. So I get 2. So I have f of negative 1 equals 2. Let's see what f of 1 gets us. 2 times 1 cubed minus 1 plus 3. So 2 minus, this goes to 1, 2 minus 1 plus 3. And that gets us 4. So this is what we have it here. I'm running out of space. F of 1 equals 2, and f of 1, negative 1 equals 2, and f of 1 equals 4. Right? And does our thing fit in between that? Yes, it does. So we're set. So all we're going to say now is f of negative 1 equals 2 I'll probably say since, make this like a story. Since f1 equals 2 and f of 1 equals 4, then, right, what are we looking for? 3.5? Doesn't that fall between those two? So we don't put 2 and 4. What we put is f of negative 1 is less than 3.5, which is less than f of 1. Right, notice again, I don't use the actual value, I use the function because we want to tie it into what we're doing. So f of negative 1, which I know is 2, is less than 3.5, which is less than f of 1. So there must be a c within the little interval they gave us, negative 1 to 1, such that f of c equals 3.5 by IVT. Right? So same process. Show it's continuous. We did that. It's a polynomial function. Right? Find the two values to make sure it works. Right? So we do. In this case, I did f of negative 1 and f of 1. I got 2 and 4. They want to show that a 3.5 fits. It does. 3.5 is between 2 and 4. So you just say that. Then f of negative 1 is less than 3.5, which is less than f of 1. So now we're done. Right? You gotta go, okay, I got the thing I want. So there must be a c in between the interval we had that falls in, right? Again, all they're saying is, hey, I have a point right here. Negative 1, 2, and 1, 4. And they're asking, does there have to be a point at 3.5? This is 2, this is 4. Well, yeah. Again, but IVT says, right, you're going to have to cross there at least once. At least once. So there must be a c between that two intervals such that f of c equals 3.5 by IVT. So that's the idea. Let's do a couple more IVT questions, this time in AP style. Ooh. So this is the first one here. Temperature FT in Arizona was recorded every 30 minutes for a 3-hour period, beginning at 7 a.m. So all they're saying here is that this, see how it says temperature minutes? So this is 7 a.m. And then you add 30 minutes, so 7:30. Right? 8 a.m. another 30 minutes, so it'll be 8:30. They add another 30 minutes, something 9, 9:30, and then 10. So that's all they're saying. That's what those values mean. And this is the temperature in Fahrenheit. Is there a time T between 7 a.m. and 10 a.m. where the temperature in Arizona was 80? Explain. So the thing we got to know here, remember, if we're going to use IVT, the first thing we got to say is it continuous? And in this case, temperature is continuous. So when you give you a real life problem like this, most things in real life are continuous. Time, right? Temperature is continuous. Time is continuous. Things grow continually, right? A tree doesn't just hop from 5 inches to 10 inches. All this stuff is continuous. So when we're talking about a real life problem, it's going to be continuous. You just say this is continuous. So in this case, I'm going to say temp is continuous. Temperature is continuous. Right? It is. You can't skip from 70 degrees to 72 degrees. It can go up in progress. So where is it equal to 80 at? So we're going to do the same idea, right? We want to find 2 points, one that's below 80 and one that's above 80. So in this case, if we look here, look right here, right? We have at 8:30, it was 78 degrees, and then at 9, it was 83 degrees. So there we must have got past 80 at some point there. So that's what we're going to say, right? At f of 90, it was 78 degrees, and at f of 120, it was 83 degrees. So same thing we did before. So f of 90 is less than or equal to 80, which is less than or equal to f of 120. So there exists, I'm going to use t because we're talking about time, a time t in between, so was it 90 and 120? I can also put, if you want to also put the time, you can say like 8:30 and 9 a.m. if you're fancy, where f of t equals 83 by IVT. Right? So it's always the same process, right? It's continuous. What endpoints do I have that fit the interval I want? State that. Say, hey, there's a t such that, or c in that interval where f of t equals 3 by IVT. It's always kind of the same concept. Just gotta get used to writing that stuff down. And our last one here, So with the little twist on it, let g of x be a continuous function on an interval from -2 to 3. What is the minimum amount of times g of x equals 0? So we're going to do IVT, but we're going to also add in that the existence of 0 theorem. So again, let's go. We're going from -2 to 3. So from here all the way to there. They want to know how many times, what's the minimum amount of times g of x equals 0. So I always tell students, if you're having a hard time seeing that, just plot it real quick. -2, 4, -4. Plot it correctly real quick. -1, -2. 0, 1. 1, 3. So 1 right there. 2, -1. 3, -5. So, right, so that's my picture. Remember, it's a continuous function. So that means we have IVT, we have existence of zeros, right? What does that mean? That between any 2 points, all the y values get to you. So we're going to have a 0 in between here somewhere. And between these two, right, we're going from positive to negative. There must be a 0 in between there somewhere. So if you look at this, it's 2. 2 is the min amount of times. Now, why is it the min amount of times? Because remember, you know this is a continuous function. I have no idea what it looks like. My graph, let me draw that thing kind of again, could be crazy and go all over the place. That's not the best example. I didn't really change it that much. Right? Who knows what goes on between these things? I could be doing this the whole time, right, and have a lot more. But at the bare minimum, if you kind of connect it, it's 2. Now, I still got to justify my answer. How is that? What's happening at? So it happens when it switches from negative to positive, so here, and from positive to negative here. So I'm going to use f of 1 is less than 0 is less than f of 0. This is negative, and this is positive. Now, and the one over here, now switch. So I'm actually going to go f of 2 first, because that's a negative. F of 2 is less than 0, which is less than f of 1. So there must be a 0 in between 1, 0. I guess there must be a c in between 1, 0 and 1, 2, such that f of c equals 0. So something to that effect. And that's how we use IVT.